Hi there and welcome to the screencast for workshop 3 for 161122 statistics. So we're going to start by running the code here in order to generate a histogram. And you can see here that when we generated the histogram, we have a message spat out that says stat bin using bins equals 30, pick a beta value for bin width. And you notice we get this very strange looking histogram where we have gaps. Okay, and gaps that happen reasonably consistently. And that's essentially because these data are rounded. So if we go in and have a look at the quakes data, then we'll see that if you have a look at the magnitude, it's rounded to the nearest one decimal place. Okay, so when we divide the range up into bins for our histogram, it could be, you can see that because we've chosen 30 bins, there's approximately 5 bins between 4 and 4.5. So there's a bin around every 0.1, and our data is about every 0.1. In fact, if you actually count them, there's actually 6 bins between 4 and 4.5. So one of those bins probably has no observations because there's only 5 possible values in between, and we've got 6 bins, so that's the pigeonhole principle, right? You've got 6 pigeonholes and 5 pigeons. One of the holes must be empty. Okay, so one of the bins here must be empty. So that's what's happening. So we may want to vary the number of bins. So we can do that by specifying the number of bins. So we can just do that by adding on another parameter to the histogram function. So we separate it with a comma and we just say bins equals, say, 20. And you can see that I get a very different shape. I've got this big spike here just after 4.5. What about if I go bins equal 25? Then I get a different shape again. Okay, so what's going on here? Well, one way to tell what's going on is to look at the actual underlying data. So 25 bins gives another again. Okay, so let's see why this is happening by adding a data rug to the plot. So a data rug is just so perhaps we'll go back to the original one and we'll add on a geom rug. Okay, so let's see what that does. You can see here's the rug down the bottom here. So this is just a little tick mark where we have data. Okay, so you can see that some of the tick marks are a bit thicker. That's because there's multiple data points at each one, and so depending on the rendering number of pixels used, some of them look a bit thicker. So that's just an artifact of the plotting. But what you can see now is we can see why these bars are empty. These bars are empty here. They have no count because there's no observations that fall in that range. Okay, so we can clearly see here from the rug that our observations are rounded, appearing only at every 0.1. So the bar that starts a little higher than 4.0 and stops a little bit before 4.1 contains no observations. Okay, and we can see this when we do the when we specify the number of bins. So let's switch to bins equals 20 again. Right, so you can see that this big spike here is because we actually have 2 observations here. We can perhaps see it a little bit better if we turn the fill to NA, which should make it not fill. Oh, we've got to add a color though, so we can see the outline. Right, so what I've done is I've changed the inside of the bars to be nothing and changed the outside of the bars to be black. Okay, I could have put another color here, so we could have gone with, pink or whatever. Let's go with orange. Okay, so you can see here that this bar that's super high actually has two observations landing in it. So you've got the observations at 4.5 and the observations at 4.6 are both in that bar, whereas most of the other bars only have a single observation hanging in it. Okay, perhaps with the exception of this one here. So this one I think has 2 bars, and this one has 2 bars, and so does this one. So these ones here all have 2 sets of observations. So because of that, of course, their height is about double what you'd think that they would be, right, compared to the other ones, because you're counting twice as many observations. The very tall bar between is covering observations of magnitude 4.6 and 4.5 and 4.6, so it's counting them both, whereas most other bars are only counting observations at a single value. Okay, so so this is a consequence of the rounding. When data are rounded, changing the number of bins in a histogram can dramatically alter the shape. So generally, a histogram isn't ideal for these data. However, we can work around this by specifying the bins so that they align with the rounding in the data. Okay, so we can do this by specifying the boundary between bins to be in between our data points. E.g., we want them to be halfway between 4.0 and 4.1, so we want them at 4.05, for example. We then specify the bin width rather than number of bins, so that our bins all start in between observations. Right, so in this case what we're going to do is same thing. We are going to, instead of specifying the number of bins, let's put these parameters on separate lines just to break it up a bit. Okay, R ignores white space generally, so this will work just the same. Now what we want is we want the bin width now, so we could choose 0.1 so that we have 1 bin per observation, that would be fine, but then we want our boundary to be at 0.05. Okay, so let's try that. So now you can see that I have my boundary and my bins are directly centered over my observations. I think you can also specify the center rather than the boundary. Let's have a look at the help. So we can specify bin width and bins. Let's have a look. What else can we specify? Bin width, bins. So either the center or the boundary. Okay. Right. So we could have we could also specify the center is equal to 0, for example, and that would give us the same plot. Okay. Because the first, so a bin, I mean, we could put the center equals 4 as well, just to specify that we want a center to be, we want a bar to be centered on the observations at 4. Okay, we could also increase the bin width from here, right? So when we change the number of bins, we'd want to increment it as a multiples, just so that we make sure that we're always capturing actually that's not going to be right, is it? Again, this is going to have the same problem, isn't it? Which way does the observation 4.1 go? Does it go into the 4.0 bar, or into the 4.2 bar. So that's not what we want. We want our boundary to still be at 0.05. That's better. Okay, so this ensures that we always have two sets of values in each bar, except of course at the ends, where we just don't have any observations below 4. Okay, so that's how you can get around the case where we have rounded data. Okay, perhaps generally a better option than the histogram is a density. So let's have a look at that. Is a kernel density estimate plot or density plot. This can be thought of as a smooth version of a histogram. It's constructed slightly differently, but the same basic idea applies. So there's the smooth version of the histogram. This looks like it might be slightly over smoothed, right? If you compare it, I mean, perhaps it's not. If you compare it to this one, it is capturing the shape reasonably well, isn't it? But perhaps it's this one here is picking up that there's a sort of a little bump out here. Is that picked up in the density? Oh yeah, it's picked up in the density. So perhaps it's not too bad. We can alter the amount of smoothing by using the adjust parameter. Right, so just like we could for density 2D, which we looked at last time, we can do the same thing here. So if you put a value lower than 1, will smooth less. Perhaps we'll make it even smaller so you can see what's happening. Okay, so you can see here what must be going on is each of these shapes here is the shape of our little blob, our kernel that we're putting on each data point. Okay, if we add the rug, okay, you can see that each of these kernels, each of these little blobs has been centered on the data. So all we do when we generate the density is we put a little blob on each observation and add the blobs up, and where they accumulate is where you get sort of hills. Okay, so this is 0.3 is certainly not enough smoothing. It is massively under smoothed, but it does show how the kernel density is constructed by placing little blobs on top of each data point, or centered on each data point, I guess. Then accumulating these blobs up into hills. Okay, so we might want a little bit, we might want a bit more smoothing than that. Let's try something bigger than 1. So we could try 2, for example. Okay, that's probably over smoothed. We're losing detail now. So perhaps we might want something else. Let's try 0.8. This is starting to capture. This is still capturing the trend. Most earthquakes are around 4.5 magnitude, or most common for earthquakes to be around 4.5 magnitude. Range is from 4 to 5.5, and most occur between 4 and 5.5, a few higher around 6 to 6.5. Right. So this is slightly skewed to the right, okay, where we have a longer tail out on the right side, but that might just be a property of the data because it stops at 4. So presumably there's magnitude earthquakes that have less than magnitude 4, but perhaps they're just not in the data set, right? So this could be truncation due to the way the data was collated. So it may not be that the distribution may in fact be quite symmetric, it's just that we've lost this data. So okay, so that's the density estimate. And notice that we can make the same conclusion that I made here. So that the most common is around 4.5, and most of them lie between 4 and 5.5, with a few up to 6. We can make that same conclusion back with our histogram, right? Even some of the poorer histograms that we generated, we're still sort of making that call, okay? So the key really is that we want to come up with the visualization, the chart that best represents the shape. So personally, I think this one's quite good. Similarly, this one here is fine. That one there is fine. That one's too undersmoothed, obviously. This one's clearly undersmoothed. This one's probably over-smoothed. That one's probably okay. All right, so all of these are probably fine. So we could also try a box plot. So you remember a box plot shows the 5-number summary. So min, lower quartile, median, upper quartile, and max. So same code. We'll just change the density to box plot. Okay, and we get this here. Okay, so again, our conclusion's the same, right? In that most of the magnitudes are around 4.5. So we know that half the data is between about, 4.3 and 4.9. And then a quarter of the data are below 4.3, and a quarter of the data are above 4.9. Okay, so conclusion here is roughly the same. Most earthquakes are around 4.5 or 4.6. Around half are between the quartiles inside the box. A quarter to the left of the box, so below 4.3, and a quarter to the right of the box. above 4.9. Okay, so again, this looks to be a bit skewed to the right. However, we notice that the median is actually bang in the middle of the box. Okay, so usually when you have data that is skewed to the right, the median will be a bit to the left, right? So that essentially everything to the right of the plot is bigger than everything to the left. So you'd expect the distance here to be bigger than the distance here. So the tail to the right to be bigger than the tail to the left. But you'd also sort of expect the data inside the box to also have that same behavior, right? Where the stuff above the median but below the upper quartile would take up more space than the lower quartile to the median. Just because everything's sort of been stretched out to the right, you would expect the median to be a little bit to the left. Again, remember that these data are likely truncated at 4, so we're not getting a true representation here. As we don't have all earthquakes. Okay, now what about these observations that it's singled out here? So potential outliers or extreme values. It's somewhat arbitrary though. What happens is the software takes the length of the box, which is the interquartile range, stretches it by 50%, i.e. 1.5 times IQR, and takes that distance above and below the box. Right, so you take this distance inside the box, the length of the box, stretch it out by 50%, and then take it above the box. So you'd get a line up here somewhere. Okay, and then you anything past that bound is then a potential outlier. Okay. Or extreme values. Okay, they're not actually outliers, because we don't know that, right? An outlying point is something that's a little bit strange. Like, so for example, if I had just one point here and I didn't have these three here, then I might call that an outlier because it is extreme compared to the next observation, right? The magnitude is almost, a full one higher, right, than the previous observation, which is back here. But because I've got sort of ones periodically in between, these are probably just the large earthquakes, right? So there's nothing necessarily much larger about this one compared to this one. Obviously, this is actually an exponential scale, so the magnitude appears in the power of the energy that's produced by the earthquake. So the difference between a 6.3 and a 6.5 can be quite big in terms of the actual amount of energy used. But of course, the outcome depends on a bunch of other things. So the outcome depends on how shallow it is and which direction it's coming from and all sorts of stuff in terms of how buildings respond to earthquakes and so on. Right, so in this case I probably wouldn't say that there was anything wrong with these observations, like they're unlikely to be misrecorded. They're just the biggest ones, right? And it's just the sort of the arbitrary procedure here by the box plot that singled them out. Okay. Right. So we could play with the colours. So what does colour do? So colour is the outside of the box plot. Okay, and fill is the inside of the box plot. Okay, there's a very ugly box plot, isn't it? The default colour green is that sort of super intense sort of almost neon-y green colour. Green 4 is a bit more pleasant, and so on. So there's various numbers that you can put in there to get slightly more pleasant coloured greens. That is still extremely ugly. Same with the density. Okay, so if we just switch to a density, then the same property. So orange is the outside colour and fill is the inside colour. So I quite like adding some alpha here if I'm going to colour things. Okay, and you may want to potentially turn off the outside line. So I think you can do that with colour equals NA if you want to. So it sort of depends on the circumstance as to what you're doing, what the colour of the background is, what the look you're going for is, and so on. Okay. So lastly, so I'll just add a note there. The line for the density by specifying. So let's have a look at depth. Alright, so we're going to do the same thing. Perhaps we'll do a histogram. So there's the depth. So we notice immediately that we have 2 humps. Okay, let's try changing the number of bins. Okay, we're largely getting the same distribution. Okay. Again, these the data are rounded, but because there's a big range, it probably isn't altering things all that much. Okay, what about a density? So there's the density again, picking up the 2 humps. Let's add the rug in, just so that we know where the data points are. Okay, so again, you can see it even in the rug right there. You've got quite a lot of density here and not much in between. So it seems as though the earthquakes, let's perhaps dial the smoothing down a bit. That's probably too much. Maybe like that, that'll do. The histogram and density clearly show 2 humps. So earthquakes tend to either be shallow or deep and not much in between. Okay, so that could be a property of the Earth's crust around this region, right? And this might be picking up sort of the bottom of the crust, and this is picking up movement in the top of the crust or something. I don't know enough about geology. But, you know, that's a statistician's theory on earthquakes. I need to ask my colleagues. Some of them know a lot more about earthquakes than me. So, in this case, because we've got 2 bumps, a box plot's not going to be appropriate. Right, so if we have a look at the box plot, then the box plot suggests that when we look at a box plot, we see the box, right? Which suggests to us a single mode or hump. But these data have 2. So where the box is actually where the data aren't, right? So the data are actually, below 200 and above 500. There's not actually that much in between, whereas the box is telling us all the data is in between. Okay, so whenever you see a box plot that looks like this, right, where there's sort of this huge long box with very short tails, it typically means that you don't have a unimodal distribution. Okay, you've got a bimodal distribution. Okay, what about the other one, which is stations? So we should use a density or histogram. Okay, so let's just grab that same code that we had before, and we'll just switch to stations. Okay, so stations is clearly skewed to the right. Which makes sense as its a count. And so the count, as it's a count that plausibly could be low. In this case, I think it's at least 20, at least 10. That's probably data truncation. Right, they've probably eliminated earthquakes that have been detected, fewer than those, which are probably the small ones, which has possibly happened just by filtering out the earthquakes that are lower than 4 magnitude. So the counts can't be less than 10. So the data will tend to bunch up there. Okay, so a box plot would still be okay here. We don't have 2 humps. I think this is probably smoothed a bit much. Let's under smooth. These bumps here are probably artificial. Maybe not. So that's less smoothing there. Let's try a box plot. We'll perhaps fill it with purple. Why not? Don't need the rug. There we go, there's the box plot. So this is strongly skewed to the right. So this is classical skew to the right. Notice that the tail here is, so the right tail is longer than the left tail, but also within the box, the distance between the median and the upper quartile is larger than the distance between the lower quartile and the median. So you can see that most of the data is bunched down to the left, and that the whole thing has sort of been, it's like they grabbed the tail here and stretched it up to the right. Okay, so it's called skew to the right, where extreme values tend to be only on the right tail. Most of the data are bunched on the left. Right hand tail greater than, longer than the left hand tail, and the median is to the left of the box. Okay, so this is typical skew to the right stuff. Okay, so if you get the situation where the median is actually to the right of the box, then that may be indicating that something else is going on and it's not purely skew. So for example, data truncation could be the answer. Okay, there we go.